Hi, my name is Dr. Michael Wood. I am a professor at Canisius College in the physics department, and today's lecture is on elastic collisions, where we take two masses, m1 and m2, crash into each other, bounce off, and then move away at different speeds. And so I've kind of drawn a little cartoon here showing mass 1 moving with an initial velocity v1I, crashing into mass 2. Let's say it's at rest, it's not moving, so its speed is 0. And then they crash, and then they bounce off each other, and they leave with mass 1 leaving with a final velocity v1f, and mass 2 now gains a speed and moves away with the speed of v2f. So the speeds after the collision can be calculated with these equations right here, which we derived in last class. What I wanted to take a look at was a specific example, one that's near and dear to my heart as a nuclear physicist, and that is, how am I going to stop neutron radiation? So if I think about it, I could do something like take a neutron and collide it with a big lead nucleus. And let's say that lead nucleus is at rest. It has a speed of 0. The neutron has some initial speed v1I. And I want to find out what is that neutron speed v1f after the collision. Well, the lead is made up of 208 protons and neutrons, and the mass of a neutron is pretty much the mass of a proton, which means that the mass of lead is essentially the mass of 208 neutrons. So if I plug that into our equation that I wrote right up here, what I get for that speed of the rebounding neutron is mass of the neutron minus mass of the lead divided by the mass of the neutron plus the mass of the lead times the initial speed plus 0, because I said the lead is at rest right here, so that's 0. So if I put this in, what do I get is a final speed for this neutron, which is basically 1 minus 208 divided by 1 plus 208 times the initial speed of the neutron, which gives me a minus 207 divided by 208 times the initial speed. The minus sign means that it bounces off and moves in the other direction. And so what happens is this neutron essentially hits my lead nucleus, bounces off at basically 99% of its initial speed. So it doesn't slow down. All I've done is bounce this neutron against the wall. Whereas if I do something like bounce this neutron off of a hydrogen nucleus, so now the mass of my neutron is now bouncing off of a proton, which has about the same mass. And so if I put those in to my equation I had before, then the final speed of the neutron is the mass of the neutron minus the mass of the proton, which is essentially the mass of the neutron, divided by the mass of the neutron plus the mass of the proton, which is the same thing as the mass of the neutron, times the initial speed plus 0. So you notice that this actually disappears. So what happens in this case, since a neutron and a proton are pretty much the same mass, the neutron comes in, hits the stationary proton, they collide, the neutron stops, and the proton then zips off with pretty much the same speed as the neutron. So if you want a shield from neutron radiation, don't use lead. All you do is get neutrons that bounce around the room and eventually will hit you. Instead, use a shield of something like water, which is what we do. We put all of our radioactive materials that we don't want in big pools of water.